All right, so in this next lesson, we're going to dive in a little deeper with gases. So we introduce gases. Last unit talked about what gas pressure is, how gas exert pressure. This unit will focus on the factors that affect pressure, and we'll look at relationships between properties of a gas. So let's start with pressure. There's a figure in your book on page 453. Remember that gases exert pressure when they collide with the walls of their container. So that outward force that the particles exert on the walls of their container is called pressure. Pressure is defined as force per unit area. So some force applied to some area. If you increase the force, the pressure increases. Likewise, if you decrease the area that force is applied to, the pressure will also increase. Pressure is measured in several different units. The SI unit of pressure is the kilopascal or kPa. You have torricelli's or torr. Remember that torr and millimeters of mercury are the same thing. And then probably the most commonly used unit of pressure in chemistry is the atmosphere. Temperature can also be measured in different units, primarily measured in Celsius in the laboratory, yet the SI unit of temperature is the Kelvin. Now, something very important, anytime we're doing calculations with gases, the temperature must be in Kelvin. So this is important because the temperature will be measured in Celsius, but in order to use that temperature in a calculation, we must first convert it to Kelvin. So I'll show you how to do that in a little bit. All right, next up, to compare gases on the level playing field, so to speak, of the same conditions, scientists have come up with some standard temperatures and pressures called STP. And so here are the values for standard pressure, SP, and standard temperature, ST. So in kilopascal, standard pressure is 101.3. In both torr and millimeters of mercury, 760. Notice I put a decimal there to make it 3 sig figs. And then atmospheres, standard pressure is 1.00 atmospheres. Standard temperature, 0 Celsius and 273 Kelvin. So anytime we talk about a gas at STP, it means these conditions: 1 atmosphere of pressure and 273 Kelvin. All right, first relationship we're going to look at is the relationship between the amount of a gas and the volume of a gas. So it says here number of particles or moles, which is the amount of the gas, versus the volume. So if we're looking at the relationship just between the amount of a gas and the volume, we need to hold some things constant. So we're assuming that the temperature is constant, and we're also assuming that the pressure is constant. So imagine this. Let's say you had a balloon filled with air. How is the pressure, what is the pressure inside the balloon compared to the pressure outside the balloon? Well, if we're talking about a latex balloon that has a flexible walls, the pressure inside the balloon is the same as the pressure outside. So let's just say it's 1 atmosphere of pressure inside and outside. Now, what were to happen if you were to put more air in the balloon? Well, what would happen is the pressure would remain the same because it's in a flexible container. So even though you're adding more gas, the pressure would remain 1 atmosphere. But what would happen? Something would happen to the volume. So you're going to have more collisions. If there's more gas particles, there's going to be more collisions. But if those collisions are occurring inside a flexible container, then the pressure does not change. What's going to change is the volume. So the relationship between the amount of a gas and volume is known as Avogadro's law. That's a mathematical relationship that I'll show you later on. Says the number of particles of a gas or moles of a gas is directly related to the volume, meaning if you increase the number of particles or increase the moles of a gas, the volume will also increase. Conversely, if you decrease the amount of a gas, so if you let some of the air in that balloon out, then the volume will also decrease. So let's take a look at some examples. And I'm going to set this up a little different difference today, then I will show you another method tomorrow or the next day. So it says 1.25 moles of a gas occupies a space of 2.00 liters. What would be the volume if 0.25 more moles of gas were added? So I'm going to start off with, since we're given the amount of the gas that we're starting off with, and we're given the amount of the gas that we end up with, I'm going to start with the volume. And what I'm going to do is I'm going to multiply this volume by a ratio of moles. So you always want to multiply by a ratio of whatever is changing. So what's changing here is the amount of the gas. And that change in the amount of the gas will cause the volume to change. So let's analyze what's going on here. So you have 1.25 moles of a gas. You're going to add more gas. If you add more gas, what effect will that have on the volume? Well, given that moles and volume are directly proportional, increasing the amount of gas will increase the volume. So here's the important part. We're going to multiply the 2.00 liters by a ratio of moles that is bigger than 1 because we want this answer to be bigger than 2.00 liters. Adding more gas is going to result in an increase in the volume, and so our ratio of moles needs to be greater than 1. So be careful. This is not how much gas ends up in the container. This is how much you're adding. You start with 1.25 moles, and to that you add another 0.25, so that gives us 1.50 moles. And the original amount was 1.25 moles. Again, I want the ratio of moles to be greater than 1 so that our volume ends up being greater than 2.00 liters. So go ahead and pause the video and punch this up and see what you get. Here we should get 2.40 liters. So something else to look at is how much did the amount of the gas increase by? So not just by 0.25 moles, but 0.25, that is 1/5 of 1.25. So it's increasing by 20%. If you increase the amount of the gas by 20%, how much will the volume increase by? Well, the volume is going to increase by the same amount. So 20% of 2 liters is 0.4 liters. And so that's how much the volume will increase by. All right, here's another one. Go ahead and pause the video and work this out. Pause now, please. So this time we're decreasing the amount of the gas. We're decreasing it by 15%, 0.15 moles. And so this time, because we're decreasing the amount of the gas, we know that the volume will also decrease. And so we're going to multiply the volume by a ratio of moles that is less than 1. So if we had that flipped, where we had 1 on top and 0.85 on the bottom, our answer would be greater than 5 liters, which doesn't make sense. You're removing gas. The volume will also decrease, and so we want something smaller than 5.00 liters. So because of sig figs here, I believe I did this correctly. We want 2 sig figs because 1.00 moles minus 0.15 is 0.85, which is 2 sig figs. And so our volume then, final volume, must have 2 significant figures. All right, next up, relationship between pressure and volume. This is one that you investigated in the lab, so you should be very familiar with the relationship. Mathematically, this relationship is known as Boyle's law. You don't need to know the name, but do know the relationship. So, of course, in learning from the lab, the pressure of a gas is inversely related to volume, meaning if you increase the pressure on a gas, its volume will decrease. Or if you decrease the pressure on a gas, its volume will increase. And it works either way. Let's do this part first. If you decrease the volume of a gas, the pressure increases. Or if you increase the volume of a gas, the pressure decreases. So we can go either way. So let's take a look at an example here. It says 15.0 liters of a gas at a pressure of 2.0 atmospheres has the pressure reduced to 1.2 atmospheres. What's the final volume? So make sure you analyze these problems first. So what is changing? Well, what's changing is the pressure. The pressure is decreasing. So what you must ask then is if the pressure decreases, what effect will that have on the volume? Well, since pressure and volume are inversely related, we know that the volume is going to increase. So let's set it up kind of the same way as we did the other problems. I'm going to start off with 15 liters, and I'm going to multiply that by a ratio of pressures such that our final volume is greater than the initial volume. And so that means my ratio of pressures must be greater than 1. So I'm going to put 2.0 atmospheres on top and 1.2 atmospheres on the bottom. Go ahead and pause the video and punch that up. So we get an answer of 25 liters. If you decrease the pressure from 2 atmospheres to 1.2 atmospheres, the volume will increase to 25 liters. All right, here's another one. Go ahead and pause the video and work this out. Pause now, please. So here's our setup. The pressure is decreasing, which is going to cause the volume to increase. So once again, we want to multiply our volume by a ratio of pressures that is greater than 1. And ultimately, we get 1.93 liters. Next up is the relationship between temperature and volume. This is known as Charles's law. We're going to, though, use a graph of temperature versus pressure, and we're going to kind of do temperature, pressure, and temperature volume kind of at the same time. So let's take a look at this graph. So I've set it up with temperature on the y-axis. This temperature is in Celsius, and then pressure on the x-axis in atmospheres. So if we were to make a plot of the temperature of a gas versus pressure, what will we end up with? We would get something like this. I think that'll be okay. May want to change the slope just a little bit, but draw a line there. There's something I just need to show you on this graph, so that'll work. We'll go with that. All right, some things to notice from this graph. First of all, at negative 273 degrees Celsius, there is no pressure. Now, how is that possible that a gas exerts no pressure? This must mean that there is no gas movement. So the particles of the gas are not moving. The only time that this is possible is at absolute zero. So absolute zero is negative 273 degrees Celsius. Something else to notice, at 0 degrees Celsius, we have that pressure. And at 273, we have that pressure. So at 273 degrees Celsius, there is twice as much pressure as there is at 0 degrees Celsius. All right, absolute temperature scaling time, you see this term. We're talking about the temperature in Kelvin. Symbol for Kelvin is K. Anytime we're expressing temperature in Kelvin, we don't say degrees Kelvin. We just give the number and then say the word Kelvin. Celsius degree is the same size as a Kelvin. These scales are just shifted, but the size of those values are the same. Negative 273 degrees Celsius is absolute zero, which is 0 Kelvin. Therefore, to convert from Celsius to Kelvin, simply take the Celsius temperature, add 273, not 273 Kelvin, just add 273 to the Celsius temperature, and that will give us the Kelvin temperature. Example, go ahead and convert 125 degrees Celsius to Kelvin. Go ahead and pause the video. All right, so we take that, we add 273, and we should get our answer, which is 398 Kelvin. So 125 Celsius is the same as 398 Kelvin. All right, so let's look at the relationship then between temperature and volume, even though we are looking at the relationship between temperature and pressure. If we were to make a graph of temperature versus volume, it would look exactly the same as a temperature versus pressure graph. And so what this means is that temperature is directly related to volume. Let's add something here. The absolute temperature of a gas is directly related to volume. So remember, absolute temperature means the temperature in Kelvin. If you double, let's say, the Celsius temperature, the volume does not double. So the absolute temperature of a gas is directly related to volume. So if you increase the temperature of a gas, the volume will also increase. And if you decrease the temperature of a gas, the volume will also decrease. Now, just like we did before, and I didn't mention it with the pressure-volume relationship, going back to pressure-volume relationship, let's do that now. Sorry about that. When we're comparing pressure and volume only, we are assuming that the amount of the gas is constant and the temperature is constant. So the amount of the gas also affects pressure. Temperature affects pressure. So what we want to look at here is just the effect of volume on pressure. When we're looking at the relationship between temperature and volume, we're assuming that the, again, amount of gas is constant and the pressure is constant as well. All right, let's take a look at an example. What volume would 2.25 liters of a gas occupy at 100 degrees Celsius if it was originally at a temperature of 25 degrees Celsius? So let's think about this. What's going to happen? What is changing? The temperature is changing. What is happening to the temperature? The temperature is decreasing. If you decrease the temperature of a gas without changing the amount of the gas and without changing the pressure, what's going to happen to the volume? The volume will also decrease. So again, we're going to start off with our volume here, and we're going to multiply this by a ratio of temperatures such that our final volume is less than our initial volume. So that means we're going to multiply by a ratio of temperatures that is smaller than 1. So be careful, we got to take this temperature and convert it to Kelvin. Go ahead and do that now, please. Pause the video. So 100 degrees Celsius in Kelvin is 373. And we need to take this temperature and also convert that to Kelvin. Go ahead and do that. 25 degrees Celsius in Kelvin is 298. So we're going to do 298 Kelvin on top, 373 Kelvin on the bottom. Again, remember, it has to be Kelvin. You cannot do these calculations using Celsius. Go ahead and pause the video and punch that up. Now let's take a look at something. How much is the temperature going down by? It is not decreasing by a factor of 4. So we can't look at the Celsius temperature. It's going from 100 to 25. That is not decreasing by a factor of 4. The volume is not going to decrease by a factor of 4. How much is the temperature going down by? Well, it's going down by not that much. So it's going from 373 Kelvin to 298 Kelvin. So the temperature doesn't decrease by that much, which means that the volume will, I think I got this wrong. Let me fix this. I apologize for that. I read its reverse. The temperature is increasing, which is going to cause the volume to increase. So I had my ratio backwards here. So we want 373 Kelvin on top, 298 Kelvin. I misread that. I apologize for that. So temperature is going up by just a little bit, which is going to cause the volume to go up by just a little bit as well. All right, let me give you one to do on your own. Again, make sure that you convert temperatures to Kelvin. Why? Why can't you use Celsius? Well, look at this example here. If we leave our temperatures in Celsius, we're going to calculate a volume that is negative, and that doesn't make sense. So that's further evidence or further proof that we need to convert the temperatures from Celsius to Kelvin before we do the calculation. So go ahead and pause the video and set this one up. All right, so this time the temperature of the gas is decreasing. So if you decrease the temperature of a gas without changing the amount of the gas and without changing the pressure, the volume will also decrease. So our final volume is 17.2 liters. All right, this is not in the notes, but let's add something here. The relationship between the temperature of a gas and its pressure is known as Gay-Lussac's law. Again, the name's not important. What is important is the relationship between temperature and pressure. So we saw in the graph, and you saw in the experiment as well, that the temperature of a gas absolute temperature that is, of a gas is directly proportional to the pressure. So we saw in the experiment, if you increase the temperature, that will cause the pressure to increase as well. Or if you decrease the temperature, like we did with the putting the flask in the ice bath, this will cause the pressure to decrease as well. So pressure and volume and temperature have the same effect on pressure. They are both directly related to pressure. I think I said that wrong. The pressure of a gas is directly related to temperature. The volume of a gas is directly related to temperature as well. What if both the pressure and temperature of a gas change? So let's look at pressure, temperature, volume relationships. A gas occupies a space of 3.50 liters at a pressure of 750 millimeters of mercury and a temperature of 23 degrees Celsius. So those are all the initial conditions. What volume would this gas occupy if the pressure of the sample rose to 800 millimeters of mercury and the temperature rose to 32 degrees Celsius? So we're going to approach this in the same fashion that we did the other problems. Both the pressure and temperature is changing. So I'm going to take my initial volume, 3.50 liters, and I'm going to multiply it by a ratio of temperatures and a ratio of pressures. So let's go one at a time. Let's take a look at the pressure. What is happening to the pressure? The pressure is going from 750 to 800 millimeters of mercury. So if the pressure increases, what effect will that by itself have on the volume? That will cause the volume to decrease. So we're going to multiply the volume by a ratio of pressures that is smaller than 1. So let's plug in those values. So once again, because volume and pressure are inversely related, the pressure going up will cause the volume to go down. Now let's take a look at the temperature. Temperature is increasing from 23 degrees Celsius to 32 degrees Celsius. If you increase the temperature, this will cause the volume to also increase. And so this time we're going to multiply by a ratio of temperatures that is greater than 1. So let's go ahead and convert both of our temperatures to Kelvin. You can go ahead and do that with me. So 32 degrees Celsius in Kelvin is 305 Kelvin. And then 23 degrees Celsius in Kelvin is 296. So interestingly here is that we can't really predict what's going to happen to the volume. The pressure is causing the volume to decrease, but the temperature is causing the volume to increase. I suppose whichever one is changing proportionally more will have a greater effect. So go ahead and pause the video and see what you get. So it looks like the change in pressure has a greater effect than the change in temperature. Notice that the pressure changes by 50, but the temperature only changes by 9. And so because of that, the change in the pressure will have a greater effect on the volume than the change in temperature. And so we end up with a final volume of 3.38 liters. All right, here's one for you to try on your own. Notice that the volume is given in milliliters. You don't have to convert it to liters. You can leave it in milliliters if you want. Probably best to just leave it in milliliters. Both the temperature and pressure, again, are changing just like on the last problem. So go ahead and pause the video and set this up. All right, here's the setup. The pressure is decreasing. That'll cause by itself the volume to increase. So the pressure ratio is greater than 1. The temperature is also decreasing, which will cause the volume to decrease as well since they're directly related. So the temperature ratio is less than 1. And we want 2 significant figures in our answer, both because the 1500 milliliters has 2 sig figs, and then our pressures also have 2 sig figs. So we get, I don't know, 1600 and something milliliters. So 2 sig figs, we're going to round that up to 1,700 milliliters. All right, let's try one more. go ahead and give this one a try. 15 liters of oxygen gas at 27 degrees Celsius exerts a pressure of 700 millimeters of mercury. Those are the initial conditions. What volume would this gas occupy at 0 degrees Celsius and 760 millimeters of mercury? Notice anything about the temperature and the pressure? Let me reword this problem for you. What volume would this gas occupy at? Aren't those standard temperature and standard pressure? At STP. So again, be careful. Sometimes it just tells you at STP. STP are not letters. They are numbers. They are measurements. 0 degrees Celsius and 760 millimeters of mercury in this case. Go ahead and pause the video and work this out. Here's a setup. Let's go ahead and analyze. If the temperature decreases, going from 27 Celsius to 0 Celsius, temperature decreases, this will cause the volume to also decrease. So that's why the temperature ratio is less than 1. Pressure is going from 700 to 760 millimeters of mercury. So the pressure is increasing. Increasing the pressure of a gas will cause the volume to decrease. So the pressure ratio also less than 1. Cancel some units here. And we end up with a final volume of 13 liters. All right, that completes this lesson. Thanks for watching.